All right. Hello, everyone. Welcome back to Comp 3430 Operating Systems. I hope that you are all doing okay. It is suddenly cold and windy again. But I don't know, the forecast, like it started, it's happening. I feel confident that we're gonna see spring soon, and I'm really looking forward to that. Today, I promised the class that's coming after us that we would end about 5 minutes early because they have a term test, and their class, if you were here long enough to see them like flowing into the room, is fully full. And so I want to make sure that they have enough time to set up their test. So we're going to end about 5 minutes early today for this class. What I want to do today is I want to first tell you a little bit about what we're going to do today. And then I'm going to tell you a little bit about what we're going to do next week, because it's kind of related to what we're doing today. And then we'll start taking a look at some stuff related to threads and locking. So by the end of today's lecture, what I want you to be able to do is to continue to be able to describe the operating system data structures needed to manage a process and those needed to manage a thread. I still haven't managed to correct my spelling here. That extra D is a mistake. What I'm looking for us to be able to do really, really briefly today is to take a quick look at the Linux kernel source code for what it uses as a task. And I want to be 1,000,000% clear. I am not going to ask you questions on any assessment about the Linux kernel source code. I really just want you to see it with your own eyes that this is a C program that somebody wrote, and this is what the actual structure looks like for the operating system that we're actually doing stuff on right now in terms of this abstract idea of process control block, thread control block, stack, that sort of thing. I just want us to see it, and that's basically it. The other things that I want us to do today are identify the critical sections requiring mutually exclusive access to a piece of code that will run concurrently using threads or processes. The other half of this is write code that uses pthread mutex lock to protect a critical section. I've got about 5 different examples of code, and this is the bulk of what we're going to be doing today, is spending time taking a look at these different code samples, where it kind of goes from here's the textbook example of a critical section all the way up to we're using a data structure. Does this actually have a critical section in it? I wrote some code in advance of class because I don't really want to write the code in class. I just want to read it and look at it and make assessments of it. But it's all up in the Git repository for the thread management stuff. So if you want to have a copy of it and follow along, you're welcome to do that. In some cases, we're actually going to write code that uses pthread mutex lock to protect a critical section. And in other cases, I'm going to hand wave and put comments to say this is where we could lock it, but I'm not actually going to write the code to do that. Part of what we're going to be doing today is making decisions about what to lock and where to do the locking, because how we do that affects the performance of the programs that we're writing that are multi-threaded. Once we've identified these critical sections. What we're going to do next week actually kind of builds on what we're looking at here today. So today we're spending time taking a look at multi-threaded code and critical sections. And next week what we're going to be doing is continuing to take a look at locking specifically. The change from what we're doing this week to what we're doing next week is that we're going to be looking not really at pthread locks next week. We're going to be looking at locks next week. And really what that means is like what pthreads do to implement locks, how they actually implement the lock. The other thing that we're going to focus on is concurrency-related bugs. And so that's kind of the main connection point between what we're doing today and what we're going to be doing next week. Today, we're looking at concurrency bugs. We are looking at a class of concurrency bugs that are related to critical sections, and we're going to make observations about what actually happens with these concurrency bugs. Next week, we're really specifically going to be looking at a bug that's called deadlock. Many of you are experiencing deadlock right now. Many of you are experiencing deadlock where you have pipes. You got pipes, and for some reason they get stuck, and it's not clear why they are getting stuck. This is an example of deadlock, and I really want to make that connection when we get to the point of taking a look at deadlock. This is an example of deadlock, where we have multiple different things, or in some cases, one thing that's holding on to a resource, a lock in some cases, and it's unable to proceed because it can't let go of the thing that it currently has. So we'll take a look at that next week. There are many sections in this locks chapter that are not required. There's many sections in this chapter that are not required because they kind of go outside the scope of what I care about for what we need to look at for locks. The condition variables chapter here, so like I said, the chapters we were looking at this week, there's that section on condition variables, and then it doesn't really do much other than show some examples of how the code works. This chapter is a good example of like the uses of condition variables. And one of the cases where we're using condition variables is for this problem called a bounded buffer, which is a pipe. It's a pipe. It's a pipe underneath. So it's an actual thing that we would be looking at. This chapter looks pretty long, but when you take a look at the actual chapter, there are like entire pages that are just code, which is valuable to look at, but it's not super informative in terms of understanding what these data structures or what these structures are actually used for. So keep that in mind when you're taking a look at that. So what I want to do first is take a very, very quick look at this structure in the Linux kernel that's called task struct. It's called struct task struct. This is a link in the slides, if you've got the slides open on your screen, but I've also put a link to this web page in the course notes for today's lecture. So specifically, I'm taking a look here at line 785 in this file that's called sketch.h. We're going to talk about scheduling later. We're going to talk about scheduling kind of after we're finished talking about concurrency. But on Linux, the thing that gets scheduled, the object that gets scheduled is this thing right here, this task struct, struct task struct. There are a few things that I want to point at and just like emphatically gesture, look, here it is, here's this thing. The first thing is right here in the very first block of stuff. There's stuff related to thread information in this structure. There's stuff related to the state of this thing in this structure. There is a void pointer to a stack in this structure. And then I'm going to scroll all the way down, way down to the bottom of this structure because it's very big. Again, I don't care about most of this stuff for this course. I'm going to keep going and going and going all the way down to the very bottom. I'm going to keep going and going and going and going. This is a giant structure that represents everything about the things that we are able to schedule in a Linux system. I'm going to keep going and going and going and going and going and going. And I'm going to keep going here all the way down to the very bottom of this thing. I'm going to keep going here. We're at the bottom. It's 600 lines long. It's a giant structure. There's no code there. It's all structure. It's just structure. This is a giant structure. To be clear, many of these things, there's lots of if, def, and end if preprocessor flags here. You can compile a lot of this stuff out at compile time. But the very last part of this is this thread struct. And what I like about this website, this is called elixir.bootlin.com, is that a lot of structure names, you can click on them and you can see like where they're defined and stuff. This structure for this thread is all going to be defined as a struct in all of these architecture-specific folders. So this is basically the register set for that structure. This is the context for the thread that's currently executing. On Linux, and this is specifically on Linux, this struct, task struct is a thread. It is a thread. There are instances of this structure for each of the threads that you currently have running in the system, and then the properties that are inside of this structure will refer to common things when you have a group of threads that are in the same process. So they'll all refer to the same, they'll all have different stacks like we saw at the top, but they will all refer to the same address space. There's an address space variable that's somewhere in the middle of the 600 line long structure. Again, I'm not going to ask you questions about this. I really just want to point at it and gesture like, yeah, hey, look, this is here and this is cool. This is the actual thing that we're working with for these ideas of structures, for these ideas of threads and processes. But enough of that. Let's talk about critical sections. A critical section, as we saw last time, is this idea that we've got a block of code that contains a race condition. A race condition is specifically where we have two or more concurrent actors where they're performing non-atomic mutations to shared resources. Really, really generally, we got two threads that are trying to read and update something, the same thing. And they're both working at the same time with giant air quotes, or literally at the same time in some cases. What I want to do is I want to take a look at some code, and I want us to be able to make decisions about whether or not that code contains a race condition or a critical section. The code that I'm going to be working with is in this repository, so if you want to have a copy of it on your screen, if you want to follow along as I'm making changes to it, then please pull or clone a copy of this. The approach that I want to do with this is I'm going to pop this open on my terminal here. So I've already got this in this terminal right now. Inside this directory called critical sections, there are 6 examples of code that we're going to take a look at here. What I'm going to do is I'm going to show you the code, and I'm going to highlight some certain lines. I'm going to give you about 10 to 30 seconds to read the code, and I want you to thumbs up, thumbs down. Does this contain a critical section? Once we've collectively made that decision, then we'll look at what the critical section actually is, so where it is. We'll try running the examples. We'll try to make changes to them to see if we can at least correct the problem or make the output be what we expected it to be. So the very first one here is textbook sample.c. This is the first piece of code that I want us to take a look at. We've got a main function down at the bottom, and I'm going to say always the main function will not have a critical section in it. That's not something that we care about. This is entirely for setup for the problem that we're working with, and so that we can actually run it. The part that I want us to look at up here is between lines 7 and 15 on my screen. And so my question immediately is, does this have a critical section? I'm going to give you 5 seconds because this was in the textbook. And then I just want everyone to put their thumbs up right now. Yes, this absolutely has a critical section. This 100% has a critical section. So I'm going to make this code. I didn't put a makefile inside this directory. The makefile is in the parent directory. So I'm just going to make, using a different flag than I normally do, make -c and then ... So use the makefile that's in the parent directory to compile these things. And I'm going to run textbook sample. So the expected output here for me when I take a look at this code and when I was reading about this in the textbook is that I'm running 2 threads here, and so I should have twice that much as output. My main function prints out the value of that counter at the end, so I should have 2 million printed as output here. That's what I would expect to have printed as output. When I run this, I get 11060075, I get 1288861, I get 1296629, I get so on and so forth, and it changes every single time I run it. It changes every single time I run it. So yeah, this has a critical section in it, and it has a race condition. And the race condition that we're looking at in this code is on this line specifically, on line 12. Counter is this file scope variable, and we're trying to make changes to it by updating its value. So we copy a value from the whatever value it is right now, and we are adding one to it, and we are putting it back. So this is the same as counter is equal to counter plus 1, and this is 3 separate operations: load, add, store. Because we've got these 2 threads running this function concurrently, and because they're both working with the same shared variable, they can both try and load it and then get interrupted before they're able to make changes to it. So really frequently what's happening is thread 1 loads the value of counter and then gets interrupted. Then thread 2 starts, it loads the current value, it adds to it, and then it stores it. And then thread 1 will get control again, and it will add to the value that it had before, and then store that. And so what this will always look like is we're missing adds. It's always going to result in something that is less than 2 million as an output here. Thought for the reader, I'm not looking for an answer right now. Can it ever be more than 2 million? Don't answer right now, just think about it, So this has a critical section, and so what I'm going to do is I want to spend some time trying to fix this critical section, or make it at least look like the correct output. To do that, we need to start using some pthread locks. Pthread locks are going to be an object that we have to create, and in this case, all of the threads that are making changes to this thing need to be able to share access to that lock. The lock itself has to be a shared resource. I'm going to declare and initialize a lock up here. So pthread lock t is the type that I want to initialize. And the name that I'm going to give it to it, sorry, pthread mutex t. The name that I'm going to give this is counter lock. And I'm going to initialize this to be pthread mutex initializer. There's different ways to initialize pthread locks. So if I take a look at man pthread mutex lock, I'm going to zoom in on this, quit, and start it again. There's a few different ways to initialize them. There are these ones that are just kind of defined by the system. And if we do this copy, we're just going to get an instance of this type of lock. We can also call this pthread mutex init function if we want to do more complex attributes to this. But for us, we only care about having a basic thing. Yeah.
You just had an extra T.
Thanks. An extra T mutex, thanks. Thank you. Okay, so we've initialized this lock. The lock object itself, in this case, in this specific case, must be shared and accessible by all threads that are making changes to the resource that they are sharing. We can have multiple different locks in our system, which leads us to the deadlock problems that we're going to talk about next week. But for now, we'll say that if I'm going to make a lock for something, I should make a lock for that one resource that's going to be shared by these multiple things. In terms of where I place the lock to acquire the lock, so each thread is going to start running in this thread counter function. They both start running code inside this thread counter function. And so I have a couple of different options here in terms of where I place the lock. I'm going to go back over here. I'm going to quit. I'm going to make this once more. And I'm going to copy textbook sample here to textbook sample no locks. I want to have this version of the code around so that I can run some comparisons against different implementations to see how their performance is affected by acquiring and releasing locks. The first place that I'm going to try acquiring this lock is inside my loop. The critical section or the race condition is this line here. It's that line right there. So I'm going to acquire my lock right before I make this change. Pthread mutex lock. I need to pass it counter lock, the lock that I want to work with. I'm going to do the thing with my shared resource that's not atomic, and then I'm going to release it. Pthread mutex unlock. Whichever thread gets into this loop first and calls this function will get the lock. There is only one lock to share among the threads that we have. The second thread that tries to acquire this lock will block here. It gets stuck. It is not allowed to enter the critical section. What we've done by putting these here is we've guaranteed that only one thread will execute the statements inside the locked area at a time. So we've effectively turned this into an atomic operation. We've effectively turned this into an atomic operation. This is now effectively atomic. I'm going to make this. I'm going to run this. And I'll think about it. If every thread that accesses this and updates it and stores it back can guarantee that this is an atomic operation, think about what your expected output might be here. Okay, and then I'm going to run it. And it's the same every time. It's exactly what we were hoping that it would be. I'm going to run this now using this program that's called Hyperfine. Hyperfine is a tool that you can use to run code for performance evaluation, performance assessment. Hyperfine is a tool where it will run the same code a bunch of times instead of just running it once. When you run code once, it takes a little bit of time to read it from the hard drive and then start actually executing instructions. And we don't really want that to affect our measurement of how quick or slow this program is. So Hyperfine is going to run this a bunch of times. I can pass it two different programs, and it will run both of those programs separately and then compare the performance characteristics of them. So I'm going to hit enter on this. It's going to run textbook sample first, which is the one that currently has locks, and the one that has no locks. And what we're seeing here is that textbook sample no locks runs about 10 times faster than textbook sample. So adding that lock acquisition has just made our code run 10 times slower. It's made our code run 10 times slower. It sure didn't seem like it because we were just like press up and hit enter and we get output immediately. But as we increase the number of times we're acquiring and then releasing the lock inside that loop, it's going to substantially affect the performance that we've got. So I'm going to copy textbook sample one more time. I'm going to say locks in loop here. I'm going to zoom out. The other place that I could put this, I'm going to comment this line out, is I could acquire the lock before I enter the loop, before I enter the loop at all. And then I could comment this line out and acquire the lock after I exit the loop. So what this now says is the first thread that gets to go will enter the critical section area that contains this entire loop. Thread 1 will get to go, or thread 2, whichever one happens to get there first. It will run the entire loop to completion, and then thread 2 will be able to get in after it has been given the lock by thread 1 releasing the lock. I'm going to run this one more time. And I'm just going to put this immediately into Hyperfine here. So textbook sample, locks in loop, textbook sample, the one that we've got right now, and textbook sample no locks. And so what we see here is that the one that we've got where we put the locks around the loop, so one thread is allowed to go into the loop, and then the other one has to wait until that first one's finished, and then the next one gets to go, is 1.6 times faster than no locks. But I'm going to take all credibility away from this. The standard deviation here kind of says like they're close enough to effectively be called the same. This one, textbook sample, is running 15 times faster than locks in loop. But the problem here is that we've taken this multi-threaded concurrent program and we've turned it into a sequential serial program. Thread 1 will fully run through the entire loop before thread 2 is allowed to enter it. And so we've accomplished nothing. We've accomplished nothing here by protecting this critical section. Having that thread acquisition and thread release inside the loop makes it run possibly multiple threads at a time, but it takes so much time to acquire the lock and unacquire it, release it over and over and over again, that adds a huge amount of runtime to this. Yeah?
Would it be faster to, like, in the counter, initializing the thread and then locking it inside the loop, maybe?
Initializing the counter lock inside the thread?
Sorry, no, initialize the thread inside the method. And then inside the loop, we lock and unlock after we increment the count.
I guess I need to make sure that I understand what you mean. Do you mean taking line 10 and putting it inside the function?
No, I'm not entirely sure, like, what I was trying to get to.
Okay.
Well, I was trying to say, like, that essentially when you create your new thread, when you, like, you make a new thread, essentially.
Yeah.
Would it be better to put the thread inside that critical region?
So I think I understand what you're asking, but I think that your idea of this might be inverted a little bit in terms of making sure that we've got a critical section that's protected.
Mm-hmm.
When we're launching threads, we give it the code that it's supposed to start running with. We can't have the code launch the thread itself. Yeah.
Yeah, I'm missing two.
Okay, it's no trouble. Okay, so this code has a critical section. We have protected it in two different ways with locks, where one of them is effectively turned it into a serial operation, and the other one is just really slow. But they both have protected this critical section with locks. I want to take a look now at this other one, textbook sample, and I'm going to call this textbook sample modified a.c. There's two different modifications that I've made to this. Two different modifications that I've made to this sample program. And so my question for you right now is given this code, again, mainly ignoring the main function here, take 10 seconds, and then I'm going to ask for thumbs up, thumbs down. Does this have a critical section? Okay, thumbs up, thumbs down. No, this does not have a critical section. Okay, this doesn't have a critical section. The reason that this doesn't have a critical section is that this variable now that has its name duplicated, that was not meant to be a confusing part of this. Sorry if that was confusing, but that wasn't meant to be confusing. This variable now, I'm going to use this keyword. This is thread local. Thread local means that it's a stack variable in this thread stack. When we create that struct task struct instance by calling clone indirectly by calling pthread create down here, each of these things is getting its own stack. So when thread 1 starts in thread counter here, it has its own copy of counter. The counter that's being referred to in this loop then is not a shared resource. It's not shared at all. It is completely local to that thread. When thread 2 starts running through this, it also has its own stack allocated thread local copy of counter. And so the counter plus plus operation, it's still not atomic, but it's not a shared resource. So it's not a race condition here. Each of these might get interrupted mid-instruction or mid-statement, but it's irrelevant because they're working with different memory locations. The main problem with this code, if I zoom out here and I run it, modified A is that it doesn't work anymore. It's not a critical section and it's not a race condition, but neither of these threads are making changes to this global variable that the main function is actually referring to anymore. Yeah.
So in the stack, like, since each thread would increment the counter and make it 1 million, can you like just update the pointer to the address?
Can we update the pointer to the address?
Basically, take the value of the counter and copy the value to the address of the global counter.
So we could, and your idea is excellent. So excellent, in fact, that if I go to textbook sample modified B here and take a look at this, I'm going to straight up tell you that this also does not contain a critical section. And this maybe doesn't do exactly what you're describing, but it's similar enough in that we take no arguments to this function. We allocate on the heap a new memory location to store an instance of an integer. The pointer here called counter is local to this thread. And when I call malloc, each time I call malloc, I'm going to get a different address. So it's not going to be a shared resource here anymore. Within the loop, we're counting. We're doing the counter plus plus, but we're using the memory location that we got back that was on the heap. And then at the end, we are returning counter. One of the changes that I made down here in the main function for this one is that I'm taking this really awfully double pointer void pointer thing and like getting it back from that, that thing. But the add operation to put counter in the output here is in the main function itself. And this is a sequential operation now. So we don't have multiple threads of execution anymore. We just have the one main thread of execution. Yeah?
You leave the mallocs in the main function because it's already being allocated in the thread function?
Because we're passing this double void pointer here, I need to pass a pointer to an address. So I do need to have some kind of allocated memory. I might be able to do this stack allocation, but double pointers hurt my head, and I'm not really sure what else to do here other than to pass up an address of a pointer. Yeah. So I'm not sure if that exactly does what you were thinking, but the idea of basically taking these two different things, and I think, let me go back to modified A here. I think what you were suggesting is if I were to say, I'm going to change this to be outside counter, and then here we say outside counter plus equals counter. Is that what you were suggesting? Yeah. This one still would have the same problem as the plus plus operation. Because it's a load and then an add and then a store, the two of them may still run that same statement in parallel, in concurrence, run it concurrently.
When the output counter would be incremented, the counter would be like 1 million at least.
So in this case, we'd either see that it would be 1 million or 2 million. Most of the time, it's going to be 2 million. Most of the time, very infrequently, it will be 1 million. Extremely infrequently, it will be 1 million. But it's possible for that to happen. So that's a good idea. But the better idea here, again, is just make sure that each of our threads is working with their own independent work area as opposed to sharing something. OK, so I'm going to go now and take a look at another sample here. This one is called list traversal A.c. I'm going to zoom in on this code. What we can see here is that the main function creates these two threads of execution. It starts by building a list for both of them. It starts by building a list that's shared. It creates these two threads. And the function that's executing in parallel here or concurrently is this thread traverse function. So I'm going to give you 10 seconds to think about this. And my question is, again, does this contain a critical section? Okay, thumbs up, thumbs down. I see 3 thumbs down. Okay, so good. Everyone else is working on their shell. This does not contain a critical section. There's no race condition here. This thread traversal doesn't modify the list. The list itself is indeed a shared resource across the 2 threads that are iterating over it, but the way that these threads are iterating over that list is to use a thread local pointer. That's the only thing that's getting changed, is this thing that's local to each of the threads. The output from this, so when this build list function runs, it inserts this, this hello to be the head, and then it inserts world to be the head, and then it inserts a bunch of numbers to be the head after that. When we run this code, the output here, list traversal, the output is kind of like, if I run this a bunch of times, we can see that the output order changes. And that's okay, that's expected. We could say that standard output is our shared resource that there's a race condition on in terms of producing output, but that's not important to what I'm thinking about here in terms of internal data structures. The output here is going to change each time I run this, and it's going to change kind of randomly each time I run it, but I'm going to see every node output from this. That's the important part. Every node is going to be printed by both of the threads that are executing concurrently in this. I'm going to quit this, and I'm going to skip list traversal A, and I'm going to go straight to list insertion here. List insertion.c is a little bit more involved than what we've got, but it does a couple of things that I think are important for us to be able to see. The first thing that I'm going to describe to you is what it does. It starts by building a list, but this list has a head node. That's it. It doesn't put anything else into the list. It only makes a list that has exactly one node into it. After that, it then begins to populate a list of operations that it's going to apply to this list. The operations that it's going to apply to this list is it's going to constantly insert nodes to the head. Each thread that we launch is going to be passed an instance of this insertion operation. So I'm not passing this null constant here anymore. I'm actually passing something to the thread of execution, and it's going to be getting an instance of one of these insert objects. For all of them, insert after is head, and then for all of them, to insert the new node that's going to be inserted is its own thing. It's going to be allocated just for that node. I'm going to launch all the threads, and then I'm going to wait for all the threads to finish, and then I'm going to print the list out. I'm passing this thing to the thread of execution, and so in this function, we have that void arg still, and so I get that out inside by casting args to the type of thing that I pass to it. So I wrote this code, I know that I'm passing an instance of this struct, so I'm going to cast that void pointer to that structure type. My question for you here is between lines 9 and 31. I'm going to give you 30 seconds to think about this. Is there a race condition or critical section? What do you think? Thumbs up, thumbs down? Guess even. Just guess. So I see 3 thumbs up, 1 sideways thumb, and several thumbs down. This code contains a race condition. Yes, it does contain a race condition. These two lines right here, this is not an atomic operation. I'm going to pop over here. I've got thread 1 and I've got thread 2. I've got a list that has a head node in it, and that's it. There's nothing else in this. Both of them want to insert after the head node. The sequence of operations here was that we're going to change the next of the new node, the node that we're going to insert, to be the next of the thing that we're inserting after. So we're going to say that thread 1 here gets to go first. This one gets to go first, and so it's going to take its node, N1, and it's going to set its next to be heads next. And then it gets interrupted as soon as it has finished that. Thread 2 is going to start, and it's going to start inserting node 2. It's going to set nodes 2 next to be heads next. And then the next statement there was to set heads next to be the new node that we've inserted. Now thread 2 is done. Thread 1 is going to take over. Thread 1 is going to say, I'm going to set heads next to be the node that was passed to me. And so now, thread 2's node, N2, is there. It points at null. It points at the tail of the list, but it's not in the list. It's not in the list. It's just out there kind of dangling. It exists. Yes, it exists. I'm going to pop back to my code here, and I'm going to run this. The expectation that I have for this list insertion code, git checkout, textbook sample, modified A. I'm going to edit it. And I got to change this back to counter. I'm going to make this code, and I'm going to run it, list insertion, and I'm going to pipe it to this program that's called WC. WC-L counts the number of lines that get printed. In my main function, I'm printing out the list, 1 node per line. There was 1 node to start, and so I would expect there to be 10 plus 1 lines of output here. I'm going to run this. I get 11, I get 11, I get 11, I get 11, I get 11. Okay, that looks fine. I'm going to change this now to, instead of 10 threads, I'm going to launch 1,000 threads. I'm going to make it, I'm going to run it, and now I expect 1001 to be printed out each time. Okay. Did you see that there? Okay. Now I'm going to change this to be 100,000. And I'm going to make it, and I'm going to run it again, and it's going to get a lot slower. That is not 100,001. It's not even close to 100,001. But really importantly, this code ain't seg faulting. It is not seg faulting. We're just losing stuff. We're losing stuff because there's a race condition here, because we're getting into the state where we've got these threads that are getting interrupted mid-insertion, and we're losing nodes. And as we make this go bigger and bigger and bigger, we're losing more and more nodes as this thing is happening. So I'm going to pop back to my slides here. At this point, you should be able to continue to describe operating system data structures needed to manage a process and those needed to manage a thread. You have been able to some extent be able to identify the critical sections that are in some samples of code. And you have, to some extent, been able to write some code that uses pthread mutex lock to protect a critical section. We're going to keep working on this one next week on Monday, because I want to be able to start thinking about where should we put the locks for list insertion to make it actually work the way that we're expecting it to work reliably. That's it for today. I hope that you all have a great weekend, and I will see you all on Monday. Bye, everyone.